Good morning, my dear students. We have finished the first module of chemical bonding with theories of chemical bonding, and finally we finished with the molecular orbital theory. Now we move to the second module of chemical bonding, or the second part of chemical bonding. Here we have to see about ionic solvents, their ionic character, covalent solvents, Fajans rule. It goes as such. So we now move to part 2 of chemical bonding. Now we have to see what are ionic compounds. We know ionic compounds are compounds formed by the interaction of cations and anions. Or we could say when oppositely charged ions attract each other and placed in certain points called lattices, a ionic compound is formed. So in ionic compounds there exists ionic bonding, and we know ionic bonding is the electrostatic attraction which keep the positive or negative charged anions, that is the cations and anions, together in a particular compound. So usually metals react with nonmetals to form ionic compounds. That means the metals are highly electropositive, they lose their electrons. As a result, they become cations, that is positively charged ions. Nonmetals, on the other side, are highly electronegative, so they accept electrons and becomes negatively charged ions or anions. So the transfer of electrons from a metal to a non-metal result in the formation of cations and anions. These oppositively charged ions attract together and placed in the lattice or at certain distances and is called ionic compounds. See here, when we take the example, see here, sodium is combined with fluorine to form NaF. So the sodium is transferring the electrons to fluorine. As a result, Na plus is forming, F minus is forming. So Na plus and F minus attract together to form NaF crystal. We know sodium is a electropositive metal and fluorine is a electronegative metal. So the transfer of electrons creates Na plus ion and F minus ions. They have opposite charge. They are placed in lattice at separate points, separate distance, and it is called ionic compounds. So in ionic compounds, see, the ions are placed at a particular distance from each other. That particular points are called the lattice points. So because of the oppositely charged ions, these lattice points are forming. Got it? So we have to explain the formation of ionic bonds by the electrostatic force of attraction. See here, I am showing you a graph or a plot. In this particular plot, I am taking Na plus ions and Cl minus ions. And we know when Na plus and Cl minus ions come together, there are electrons present in sodium atom or sodium ion, as well as there are electrons present in chloride ions. So there exists a repulsive force between the electrons of sodium and chloride ions. So one of the force acting between these two ions are the electrostatic repulsive force between the electrons of sodium and electrons of chloride ion. The second force of attraction is between the electrons of the sodium with the nucleus of the fluoride ion, because the nucleus of the fluorine contains positively charged protons. So the electrons of the sodium ion attract the positive part of the fluoride ions, that is the nucleus. Similarly, the electrons of fluoride ion could attack the positive part of sodium ion, that is the nucleus of the sodium ion. So repulsive force is occurring as well as attractive force is occurring. And finally, the positive part of the sodium could repel the positive part of fluoride ion. So different interaction could happen between Na plus ions and Cl minus ions. So we are plotting a graph with bond distance, potential energy against the distance or bond distance. So here we have a green curve, down we have a green curve, and this green curve in the lower half shows the maximum energy would be released when ions are infinitely close to each other. That means this is the attractive interaction between the electrons of sodium ion with the nucleus of chloride ions and the electrons of chloride ions with nucleus of sodium ions. So that is the interactive attraction represented by this green graph. Then there is a red graph or red curve or red line which shows the repulsive electron-electron interaction as well as the proton-proton interaction. So after a particular distance, see, after a particular distance, the potential energy becomes zero. Then we have a purple curve. And this purple curve is the intermediate of these two green and red curve. And it shows the total energy of the system reaches a minimum. See here, a minimum at a distance r0. From r0, if we move closer, see, this is the bond distance. X-axis is the bond distance. Y-axis is the potential energy. So, after a particular distance, again the energy increases. So, this particular point at which the attractive and repulsive force tally each other to an intermediate equilibrium value is the bond distance in ionic compounds. So this distance which balance the electrostatic repulsion and electrostatic attraction termed as the bond distance between the positive and negatively charged ions. So this is the energy representation, potential energy against bond distance representation of an ionic compound. So an ionic compound at a particular distance R0, that for NaCl it is 236, that represents the bond distance between Na plus ions and Cl minus ion. Now we have to see what is lattice energy. When oppositively charged cations and anions are placed at certain points in a crystal called lattices, it releases certain energy, and this energy is called the lattice energy. So we could define lattice energy is the energy released when 1 mole of a crystal or ionic compound is formed from its oppositively charged ions. So, when these two ions are brought together at a particular distance, energy is released, and this energy is called lattice energy. So, it measures the strength of the ionic bonds. That means higher the lattice energy, greater the stability of the ionic compound. That means if a crystal emitted 100 kilojoules of energy, we have to supply 100 kilojoules of energy to break them into constituent ions. So, to find out the strength of any ionic crystal, we use the term lattice energy. But lattice energy cannot be experimentally determined. It could be estimated or calculated using Born-Haber cycle or Born-Lande equation. So experimentally it is very difficult to establish the lattice energy, but we can calculate the lattice energy easily by using Born-Lande equation or Born-Haber cycle. So lattice energy is the strength of the ionic bond. Greater the lattice energy, greater or more stable the ionic compound. Very, very important. Take down. To calculate bond, lattice energy, Born and Lande, they proposed an equation which is called Born-Lande equation, which is basically a complicated equation, but it could be used to find out or calculate the lattice energy of ionic crystals. So the equation is given as U is the lattice energy. U is equal to Na into M Z plus Z minus E square divided by 4 pi epsilon r into 1 minus 1 by n. So considering the repulsive energy and the electric potential, they have derived this particular equation. where Na is the Avogadro number, M is a constant called Madelung constant. It depends upon the geometry of the crystal, whether it is a BCC, FCC, or something like that, or trigonal, or orthogonal, or a simple cubic lattice, etc. like that. Z plus and Z minus are the charges of the cations and anion respectively. E is the charge of the electron, and epsilon is the permittivity. R is the interionic distance or the bond distance in that particular ionic compound, and N is a constant called bond exponent. So using this particular equation, the lattice energy could be calculated. So in examination, they may ask, give Born-Lande equation and explain the terms involved in it. Or what is the significance of Born-Lande equation? So Born-Lande equation is used to find out the lattice energy, considering the repulsive potential energy and the electric potential of the ionic crystal. We have seen Born-Lande equation for calculating the lattice energy of an ionic crystal. Now, apart from Born-Lande equation, an easy concept to calculate or to find out the lattice energy of a crystal is Born-Haber cycle. So, by Born-Haber cycle, we could easily compute the lattice energy from the experimental observational values. So Born-Haber cycle is a cycle of enthalpy change of process that leads to the formation of a ionic compound from its basic elemental atoms in their standard state and comparing with the enthalpy of formation of that ionic compound. So we will compare the enthalpy of formation of an ionic compound, which could be found out experimentally, and we will tally it with the different process associated with the formation of an ionic crystal from the basic constituent neutral atom. That cycle, which shows the formation of an ionic crystal, is called Born-Haber cycle. Born-Haber cycle. You could make it easily by taking the example of sodium chloride. I hope you might have seen this in your plus 2 classes, or your teacher might have taught you. I do not know whether you learned it. So we are going to take an example of NaCl, sodium chloride, and we make a Born-Haber cycle. And from the Born-Haber cycle, we calculate or compute the lattice energy. So, for the formation of sodium chloride, we have to consider different process from which a sodium atom is converted to Na plus cation in the gaseous state. Similarly, From chlorine molecule, we have to move to chloride ion. Then we have to combine the sodium ion and chloride ion in the gaseous state to form ionic crystal. So we move to the example of NaCl, with which we could explain Born-Haber cycle. The different steps associated with the formation of sodium chloride could be listed out as follows. The first step is the sodium atom, which is in the solid state, is converted to the gaseous state by sublimation. So a solid is directly converted to a gaseous state, and the process is called sublimation. And for sublimation, we have to supply certain amount of energy, which could be experimentally calculated. And this energy is the sublimation energy. So in the first step, we are converting sodium to sodium gaseous state by supplying energy, and the energy, sublimation energy for sodium is 108 kilojoules per mole. This energy we have supplied to the system, hence it is having a positive value. So we could take this as step 1, or this is equation number 1. In the second step, we have to convert the sodium from the gaseous state to Na plus ion. So here sodium is in the gaseous state, which is sodium atom. We have to convert them to sodium ions. For this we have to supply energy, and that energy is called the ionization energy. We define ionization energy is the energy applied or supplied to convert a neutral gaseous isolated atom to its ion, or to remove an electron from a neutral gaseous isolated atom. So here Na is converting to Na plus. So we are supplying energy, and that energy is called the ionization energy. The energy is supplied, hence the value is positive, positive 496 kilojoules per mole. So in the second step, we converted sodium in the gaseous state to sodium cation. Now moving to third step, we have chlorine molecule, Cl2 molecule. So it is existing in the gaseous state. I have to convert them to sodium chloride atom, chlorine atom. So chlorine molecule has to be converted to chlorine atom. So we have to dissociate the bond between chlorine. So chlorine bond has to be dissociated. To dissociate this particular bond, we have to give energy, apply energy or supply energy. See here, when we consider the bond dissociation energy, we are taking only one chlorine atom here. We are not taking two chlorine atom, only one chlorine atom we are considering for the further steps. So we have to consider half of the bond dissociation energy. See, one chlorine molecule breaks up to give two chlorine atom. From that I am taking only one chlorine atom. So I have to take half the bond dissociation energy. Half of the bond dissociation energy. That is half of 244. It is equal to 120 kilojoules per mole. So the third energy aspect is the bond dissociation energy associated with the formation of chlorine atom in the gaseous state. Next, the fourth step, we have to convert the neutral gaseous chlorine atom to chloride ion, Cl minus ion. So, to convert chlorine to Cl minus ion, it releases certain energy, and that energy is called the electron affinity. So, we define electron affinity is the energy released when an electron is added to a neutral gaseous isolated atom. So this is a neutral gaseous isolated chlorine atom. When it is adding one electron to its orbital, it becomes Cl minus. So some energy will be released during that particular formation, and that is the electron affinity. See, the value is negative. Why it is negative? Because energy is released during that particular process. So this is the step 4 or equation number 4. So we have converted sodium to Na plus, chlorine to Cl minus ion through these 4 steps. We have seen different steps for the preparation of Na plus gaseous ion and Cl minus gaseous ions. Now, these Na plus gaseous ion and Cl minus gaseous ion combine together to form NaCl crystal. During this crystal formation, lattice energy is released. So the energy released is called the lattice energy. So from step 1 to 5, if we take the total energy associated with different process, that total energy is equal to the enthalpy of formation of solid sodium chloride. This is predicted by Hess law. Hess law states that the total enthalpy change or energy change of a system is same if it take place in a single step or in different multi-steps. So, taking Hess law into consideration, we have to compute the total energy associated in different steps, that is from step 1 to step 5. And that energy must be equal to the enthalpy of formation of sodium chloride crystal. So the enthalpy of formation or heat of formation of sodium chloride delta HF is equal to minus 411 kilojoule per mole. So this is the energy of formation of 1 mole of NaCl crystal, and this energy must be equal to the total energy that happened in all the step 1 to step 5. So from step 1 to step 5, these energy should be equal to the enthalpy of formation of NaCl crystal. You got it? Take down. See here, all the 5 steps could be summarized here. This is the first step. Sodium from the solid state converted to sodium by the gaseous state. Sublimation energy is here. In the second step, sodium is converted to Na plus gaseous ion, and that is the ionization energy here. Now take chlorine. From chlorine, it is converted to chlorine in the gaseous state, chlorine atom in the gaseous state. So the dissociation energy is given here. The chlorine in the gaseous state is converted to chloride ion in the gaseous state. It is given the electron affinity. Now sodium and chloride ions combine together to form NaCl, and the released energy is lattice energy. So this process, the energy of this process should be equal to the energy of formation of NaCl, that is the delta HF of NaCl. So delta HF of NaCl is equal to the energy associated with this process. So we could say delta HF is equal to H sublimation plus ionization energy plus dissociation energy plus electron affinity plus lattice energy. These are the energies of the 5 steps that is equal to the enthalpy of formation of NaCl crystal. Substituting the values, we could calculate the lattice energy is found to be 788 kilojoules because enthalpy of sublimation, ionization energy, enthalpy of dissociation, electron affinity and enthalpy of formation are the experimental values from which we could calculate the lattice energy U. So this is the Born-Haber cycle. It looks like a cycle, closed cycle. So this is Born-Haber cycle. Very important. So I have already explained here. See, only 3 values are found to be negative. They are electron affinity, enthalpy of formation and lattice energy. All the other values are positive because that are the supplied energy while this is the released energy. From this, we could easily calculate the lattice energy because all other enthalpy can be experimentally measured. So taking NaCl as an example, we could explain Born-Haber cycle. The same cycle could be used for calculating the lattice energy of different ionic solids or crystals. You may expect a problem for calculating the lattice energy for any ionic crystal. Now we move to next topic, that is solvation and solvation energy of ionic solids. Solvation is the process which describes the interaction of solvent with the solute. We know a solution is formed by the dissolution of a solute in a solvent. When we introduce a solute to a solvent, there occurs an interaction between the solvent and the solute. And this process of reorganizing solvent and solute molecule is called solvation. So the process or the phenomenon associated when a solute is dissolved in a solvent to form a solution is called solvation. So during solvation, the bond has to be broken, hydrogen bond has to be established, or weakest van der Waals force has to be established. So different process happens there when we introduce a solute to a solvent. And this process is called solvation process. So during solvation process, certain energy is associated, and this energy is called the solvation energy. So when a solute is introduced into a solvent, solvation process occurs, and in solvation process there may be energy associated during that solvation process, and that energy is called the energy of solvation or solvation energy. If the solvation energy is positive, the process is endothermic. If the value of solvation energy is negative, it is exothermic. So exothermic and endothermic process is possible for solvation. That means energy could be released or energy could be accepted or absorbed during solvation process. And when a solute is dissolved in water, it is called hydration. And the energy associated is called the hydration energy. So when we take generally the solvent, it is solvation energy. And if you are taking water as the solvent, it is called hydration process, and the energy associated with it is called the hydration energy. So during solvation, the solute particles will be surrounded by the solvent molecule, and it is called the solvated state. For example, if I take water and NaCl, we have Na plus and Cl minus ion. This Na plus and Cl minus ion will come and interact with H2O molecule. H2O molecule is having O minus and H plus. So each Na plus is surrounded by O minus ion, that is the partial charge of oxygen of water molecule, and that is the solvated state in the solution phase. See here, we have the solvation process here. See here, Na plus ion is surrounded by the oxygen, partially charged oxygen ion. This is the solvation process or solvated state. So These are the solvent molecules which come and surround the sodium ions. Similarly, the Cl minus are surrounded by the positively charged H plus. See here Cl will minus will come, Cl minus. So there will be a series of Na plus surrounded by O negative, then Cl minus, again Na plus it will go. This is the solvated state. And we know ionic compounds usually dissolve in polar solvents because this interaction occurs. So water is a polar solvent. If this is a non-polar solvent like benzene or carbon tetrachloride, what happened? Na plus does not have any interaction there. So it may not dissolve here. So ionic compounds, when dissolved in water, the dipole interaction with the positive and negative ions break NaCl crystal to dissolved state to form Na plus surrounded by O minus ions, I mean partially charged oxygen ions, and Cl minus surrounded by positively charged ions. This process is called solvation and solvated state. Now see here, what are the factors that affect the solubility of a ionic compound? They are very simple. One is solute-solvent interaction that I already explained to you, because in polar solvents, ionic compounds dissolve only in polar solvents because they are strongly attracted by the polar solvents. So the solute solvent attractions affect the solubility of ionic compound. Second one is the common ion effect. Ionic compounds are less soluble in solvents that contain a common ion. See, I am taking calcium sulfate, and if I am dissolving calcium sulfate in a water sample having calcium ions or sulfate ions, I mean hard water. So what happens? There is already SO42 minus and Ca2 plus ion. So the equilibrium will not shift towards this side. So solubility decreases. So if the solvent contains common ions, the solubility will decrease. And the third factor is temperature. As we know, when we increase the temperature, the solubility of ionic compound increases, because usually the solvation processes are endothermic. So when we give heat energy, more solute will be dissolved. So three important factors which affect the solubility are solute-solvent interactions, common ion effect, and the temperature. My dear students, we have discussed what are ionic compounds and the energetics of ionic compounds and the different methods to find out the lattice energy of ionic compounds. Also, we discussed what is solvation energy, and what are the factors affecting the solubility. So, thank you for being with me for this online class. See you next week, same time, if your exams are not there. We have to conduct a exam a test from the chemical bonding part 1. I am waiting. Why? Because your S2 examination are on the table. So any day the date may be announced. That is why I am waiting. If it is only on January, then we will conduct the examination of part 1 of chemical bonding. But I feel it may appear in the first week of December. This is my information. I mean, the information got to me. It is not true or correct. So don't be panic. Ask with your class teacher the detailed timetable or something. If it is coming, it will be appear in your site or in your ID. So thank you. See you again. Bye.